Let's review lesson number 4 in the limits chapter. And lesson number 4 is all about finding horizontal asymptotes and using limit notations to describe horizontal asymptotes. Now, before we kind of start this lesson, there were some ideas from pre-calculus 11 where you can look at a rational function. And if you take a look at the powers on the numerator, the highest power on the numerator and the highest power in the denominator, there are certain cases where you can identify the horizontal asymptote right away. So for example, if the powers are the same, then the horizontal asymptote is really the leading coefficients being divided by each other. So for example here, in this very first question here, we notice that the power in the numerator and the denominator are the same. Therefore, the horizontal asymptote can be easily identified by the equation y equals to 3 over 2, and 3 over 2 are the leading coefficients in the rational function for the numerator and denominator. Okay, so this is where your horizontal asymptote is at when you have the same powers in the numerator and denominator. Another case is when the numerator has a lower power than the denominator, then the horizontal asymptote is at y equals to 0. A very classic case is the equation y equals to 1 over x. Clearly the denominator has a higher power than the numerator, and we know that the horizontal asymptote for this graph is really at y equals to 0 here. Okay, so over in this example here, clearly the denominator has a higher power than the numerator, so in this case the horizontal asymptote is at y equals to 0. And in our third case, this is when we have the numerator having a higher power than the denominator, then there is no horizontal asymptote. So in this last one here, we can see that the numerator has a higher power than the denominator, so there is no horizontal asymptote. In fact, for these kind of graphs, we generally have this kind of behavior when you actually have a slant asymptote, and that is the graph is actually just kind of shooting up. And we kind of call this a slant asymptote. So when your numerator has a higher power than the denominator, that's the kind of behavior your rational function will have. Okay, let's get into a little definition here now using limit notation. So the definition of a horizontal asymptote at y equals to L. So y equals to L, this is like a constant, for example, y equals to maybe 3 over 2. L is a constant there. So if we're going forever to the right or forever to the left, and if we approach that constant, then we have a horizontal asymptote. And you might want to remind yourself that this means the graph is going forever right. And this means you're going forever left. Okay, and I'll do my very best to kind of describe this kind of behavior after we do each problem here. Okay, so one thing basically the kind of limit problems we're going to do for today is that you can easily identify the technique that we're going to use for the questions in today's video because x is going to infinity. So these are brand new kind of problems here. So we want to know what's happening to the graph when we go forever to the right. And I'm going to use something called the highest power in the denominator method. And this is kind of like a language that I've kind of made up to kind of help myself remember what kind of technique to use. And if I look at my denominator, my highest power is x squared. Okay, and what I'm going to do next is that I'm going to divide every single term by the highest power in the denominator, which is x squared. Alright, so I'm going to really just change how this original problem looks like now. So I have 3x squared plus 5x, and you might want to watch this video first before you start writing out your next steps here. And my denominator is 2x squared minus x plus 4. Okay, so what I'm going to do here is I'm going to divide every single term by the highest power in the denominator. Now, if I divide every single term in the numerator by x squared, I've changed the problem. However, mathematically, if I divide every single term in the denominator by the same thing, I haven't changed the original problem. Okay, so even though this step makes the original problem look different, mathematically it's the same problem. Okay, and then from here I can start simplifying. Okay, so if I take a look at this term right here, 3x squared divided by x squared is going to be 3x. Sorry, just sorry, not 3x, just 3. It's going to be 3 because the x squares just cancel off. And then the next term is going to be plus 5 over x. And then the last term remains exactly the same, which is 2 over x squared. All divided by, and now we just simplify the denominator there, so I can see that the x squareds here cancel off, so I get a 2 minus 1 over x plus 4 over x squared. Okay, so I simplify this as much as possible, and with any limit question, the direct substitution is going to be the final step at the very end, right? So we're going to take this infinity and we're going to insert it now into the denominators there. And you might recall from one of the investigation problems, I was asking a little question, simply, what is 1 over infinity? So 1 over infinity is really just 0, okay? So if I take a look at the denominators here, the key idea is that the denominators are going to become infinity now. That's the general idea, and basically these fractions now all go to 0. And this is very unique to this problem because x is going to infinity, so now we need a brand new technique called the highest power in the denominator, and we get 3 over 2 as a final answer there. Alright, so what does this 3 over 2 really mean? Okay, so what this really means is when I go forever to the right, when x goes to positive infinity, the graph is kind of behaving in a way where it levels off with a height of 3 over 2. So maybe this height is 3 over 2, and our horizontal asymptote is at this height of 3 over 2. If I go forever to the right, it levels off to a height close to 3 over 2. Okay, so that's what that answer means. So if I go back to this grade 11 question right here, maybe in grade 11 you're asked where's the horizontal asymptote to this rational function. We know the answer is 3 over 2, and horizontal asymptotes happen when you go forever to the right and you level off to a height of this particular constant, which is 3 over 2. Okay, let's move on to the next one here. So once again, just recognize that you're going to infinity. So when x goes to infinity, basically we're asking if there's a horizontal asymptote or not. And I look at my denominator here, and the highest power in the denominator is x squared. Okay, so just like the previous problem now, because x is going to infinity, I need to recognize that I'm dealing with a brand new limits problem. Okay, and what I'm going to do here is going to rewrite the numerator. Leave a little space there. Then I'm going to look at the denominator here. And I'm going to divide every single term in the numerator and the denominator by the highest power in the denominator, which I identified as x squared in blue. Okay, so now you go to your grade 9 skills here. And you simplify each term now. So this term right here is simply going to be 3 over x plus 4 over x squared, all divided by 6 plus 1 over x squared. Okay, and with any limit problem now, you are now going to substitute x goes to infinity, right? So anytime you see an x on the denominator, all those denominators are going to change to infinity. So logically, if I just kind of show you what that looks like, you would insert these infinities. But remember, you need to use the fact that 1 over infinity is technically really 0, right? So what we're saying is this goes to 0, that goes to 0, and this goes to 0. And it turns out your numerator is 0 and your denominator is 6, and 0 divided by 6 is going to be 0. Okay, so what does this answer mean? It means when you have a rational function, I guess when you go forever to the right, the graph just levels off to a height close to 0. Okay. So when x goes to infinity, the height of this graph levels off to a height of 0. Okay, let's move on to the next one here. Once again, we recognize that x is going to infinity, so we need a brand new technique, and the technique that I use is called the highest power in the denominator. And I look for the highest power in the denominator in this case, which is x to the power of 4. Okay, so now we go to the limit here. X goes to infinity, which is 3x to the 5 minus x plus 4, all divided by 2x to the 4 plus x. Okay, and then we can divide every single term. Remember, mathematically, if you divide every single term by the same thing, you haven't changed the original problem. Okay, so I'm going to quickly just write that out. All right, and now we got to just simplify this, right? Okay, so if I take a look at this very first fraction there, 3x to the fifth divided by x to the 4 is going to be 3x. And then minus 1 over x cubed, and then plus 4 over x to the 4, all divided by, I guess we have a 2 there, plus 1 over x cubed. Okay, and now we know that x goes to infinity. So if I look at all these, let's take care of the fractions first. Just like the previous examples now, you should be comfortable to know that these just go to 0, 0, and 0. And then if you have your 3x, what's really happening is it's really 3 times infinity divided by this denominator of 2, right? And if you think about this, I mean, 3 divided by 2 is really just 1.5. 1.5 times infinity, whoops, 1.5 times infinity is still a very big number, so this is really infinity there. Okay, so that's your special case, and just like I mentioned, I kind of touched upon this at the start of this video here, but this kind of graph is behaving in a way is if you go forever to the right, the graph is just shooting up. Okay, so when x goes to infinity, this graph is also just shooting just straight up, right? So that's what's happening there, and this is also very similar with things like y equals to mx plus b, right? If you go forever to the if you have a positive slope and if you go forever to the right, the graph is actually just going straight up, right? So that's what's happening with this particular graph. Okay, let's move on to the definition of a horizontal asymptote now. So at the start, I gave you this definition right here, and sometimes I feel like when this is being covered at the start, maybe this idea may not be clear, the definition of a horizontal asymptote using limits. So let me give you a little example right here of how to write the equation of a horizontal asymptote using limits to justify this. Okay, so what I'm going to do first here is back in your pre-Calc 11 days, if the teacher asked where is the horizontal asymptote on this graph of y equals to f of x, if I just examine this, here is my horizontal asymptote, I believe. And if I look at my graph here, and if I keep on going forever to the left here, I guess the horizontal asymptote is at this height of y equals to -4. All right, so my horizontal asymptote is at y equals to -4, right? However, in Calculus 12, we have a different way of kind of writing this idea out, and we have to use limit notation here. So if I write the limit for this graph, the horizontal asymptote happens when you go forever to the left, right? So if I look at this graph, I mean, when x goes to negative infinity, meaning I'm going forever to the left, that's where we see the horizontal asymptote. All right, so our function here levels off to a height of -4. Okay, so this is how we can write a horizontal asymptote using limit notation. And this 4 is really like that L that you saw at the beginning of this lesson here. And whether we go to negative or positive infinity, as long as we're leveling off to a height, that is our horizontal asymptote. Okay, so that's the difference between writing a horizontal asymptote in Calculus 12 compared to pre-Calc 11, where you can simply write the equation of the horizontal line and you're done. But in Calculus 12, we do have to use limit notation to describe a horizontal asymptote. Okay, great. Let's go on to a final question here. Find the following limits, and you'll notice in this question we have a square root on the denominator here. Okay, so this is actually a little bit more of a challenging question. I feel like the first 3 questions that we covered were not too difficult, but for this particular question, you need to know a few calculus theorems. And the first theorem we have is that you need to understand this idea here where you have the square root of x squared. And this came up in your in-class assignments from before. And if you graph this function, you'll notice that it's the same thing as the absolute value. Okay. Now remember, when you're dealing with the absolute value, a lot of students are having a hard time just kind of understanding that in Calculus 12, you have to understand the function idea of an absolute value. All right, a lot of students say like when you have a negative number, and if you take the absolute value of it, you get a positive number. And I'm not really referring to that idea right now. I'm referring to the actual graph of the absolute value function here, right? So when you go to positive infinity, or when x is greater, this kind of means when x is greater than 0, you're dealing with the function y equals to x. And when you're going to negative infinity on your graph, this means when x is like less than or equal to 0, you're dealing with y equals to negative x, right? So these are the functions that we're dealing with, okay? So a lot of students are saying, hey, Mr. Yoon, you know, like here is negative 6 and that the absolute value is positive 6. I'm not referring to that idea. I'm referring to the actual function notation here. And absolute values, they really have basically absolute values. You have to turn them into functions, right? So absolute value can be x or it can be negative x, depending on whether you're going to positive or negative infinity. Okay, so let's take a look at this example here now, and I'll make references to the absolute value function when I have to. And first of all, I recognize that x is going to infinity, but I also recognize there's a square root here. Okay, so whenever you have a square root, and when x is going to infinity, you have to use a different technique called the highest power. I'll say SQ, meaning highest power in the square root. And I see an x squared there and the square root sign, so I write this out as the highest power in the square root as being the square root of x squared. Okay, so I recognize that there's a square root, and the highest power in that square root is x squared. Okay, so this is what I'm going to do here. Just like in the previous problem, I am going to start off by writing my limit statement here as x goes to infinity. I'm going to write out negative 3x plus 1, all divided by the square root of 4x squared plus x. Okay. And what I'm going to do now is I'm going to divide every single term now by the highest power in the square root. And the highest power in the square root I've written as this red square root sign with the x squared. Okay. So what I've done is I divided every single term in the numerator by the square root of x squared, and I've also divided the denominator by the square root of x squared. One thing I want to just let students know in advance is that sometimes when I ask students in the beginning, when you have a square root, like we have on the denominator, what are some algebra methods to kind of manipulate the square root? A lot of students say that you square this particular case, but that does not work, because when you have like squares, for example like this, a lot of people say, hey, you can square that and that means you guys square that side, but we're not dealing with an equation here, right? So you can't just simply square this particular example here. And when you're dealing with square roots, there's a few ways you can manipulate them. So if I just give you a random radical here, like x squared plus 4, I mean, you can manipulate this by timesing this by another radical, right? You can maybe times it by itself, or another method you can do is you can divide by another radical, all right? And if you divide by radicals, you can also manipulate them. Let me give you an example here really quickly here. If I give you the square root of 9 over 4, this is the same thing as the square root of 9 over the square root of 4, okay? So if I give you just the square root of 9, and if you divide that by the square root of 4, then this is really the same thing as the square root of 9 over 4 using a bigger square root. Okay, so one of the reasons why we're dividing every single term by the square root of something is because that way I can actually start manipulating that expression there in green. And let me start off by maybe manipulating the denominator first, because the numerator will, I'll show you what we're going to do with the numerator, because the numerator is a little bit different. But if I just simplify the denominator here, it's really the square root, whoops, that wasn't very clear. It's really the square root of 4x squared plus x divided by x squared. Right, so that's how you kind of rearrange the denominator. And on the numerator, well, I have my negative 3x, and I have my plus 1. And this is where I want you to maybe not write anything just yet, but I have the square root of x squared, and I have the square root of x squared. And what I've already told students is that the square root of x squared is the same thing as the absolute value of x. Okay, so what we're going to do next here, and I encourage you not to write this down yet, but we know this is the absolute value of x, and this is the absolute value of x. But now we have to recognize that we're going to a positive infinity, right? And if I'm going to positive infinity, which is like this case right here, I'm going to positive infinity, the absolute value is just really the equation y equals to x. So I go back to my expression here, and the absolute values, they really just become single x's, because when I go to positive infinity, the absolute value is really just this part of the graph, which is y equals to x. Okay. All right, so that's the theory behind this question, and now you can start simplifying things. So this part right here, negative 3x over x, is going to be negative 3 plus 1 over x. And then the denominator here you can also simplify, and you might just want to just wait here. I'm going to rewrite this using a two-step process, but it's really 4x squared divided by x squared plus x over x squared. Okay, and if you simplify that, I see this. I see that this x squared and that x squared, they just cancel off. So you're just given a 4, and we know that this x divided by x squared is just 1 over x. So the denominator is really 4 plus 1 over x. Okay. And then finally, you can just do a direct substitution here. X goes to infinity. So when I look at these fractions here, these fractions just go to 0. They go to 0. And now you're left with the numerator, which is negative 3, divided by the square root of 4, which is now going to be negative 3 over 2. So that's your answer for that particular question there. Okay, let's move on to the next question here. And the next question here is exactly the same, but this time we're going to negative infinity. And usually what I do is I just kind of tell everyone the steps are all the same up until this stage right here. All the steps are the same except for this part right here. And let me just kind of write this as limit as x goes to infinity. I have negative 3x plus 1 all over the square root, and this is essentially the same thing too. There's no absolute values on the denominator here. And when x goes to infinity, here for absolute value functions, so remember, when x goes to infinity here, I just want to reemphasize this. We know that we're dealing with the function y equals to negative x now. Okay. So the idea is that the square root of x squared becomes absolute value, but the absolute value has two parts, and since you're going to negative infinity here, we know the absolute value function now becomes negative x. Okay. So this right here now becomes negative x, and that's the difference between this question and the question on the previous question, right? So that's the difference right there. And if we keep on simplifying here, you'll notice that we should get a slightly different kind of result here on the numerator. So negative 3x over negative x is simply going to be 3 plus, 3 minus 1 over x all over the square root of 4 plus 1 over x. And when x goes to infinity, these fractions go to 0, and it turns out your answer is going to be pretty much the other side now, which is actually 3 over 2. Okay, so that's your answer for that particular problem there. Okay, if I just have to give you a little sketch of what this kind of looks like here, you know, when you're going to negative infinity, I guess the graph is leveling off to a height of 3 over 2, and when you're going to positive infinity, I guess the height is leveling off to negative 3 over 2. So that's what this graph looks like if you had to kind of sketch it. Okay, good. What I'm going to do now is maybe this part was covered in class or not, but I want to quickly go over lesson number 5 here, vertical asymptotes using limits. So I want to say that the definition in Calculus 12 for a vertical asymptote is when you're going to a particular side of a x value, either the right side or the left side, and you're actually going to positive or negative infinity. So this right here is your general definition of a vertical asymptote in Calculus 12, and I'll I'll try to illustrate this with a little example here. So find the equation of the vertical asymptote using limits to justify your answer. So when you look at this graph right here, if you're in pre-calc 11, you can easily find the vertical asymptote by examining the graph here. And it turns out that the vertical asymptote is at x equals to 1. Okay. Now in calculus 12, if you want to use proper limit notation and use the definition that I'm referring to, all right, let me just show you how you can write the vertical asymptote using limit notation. And let's go ahead and write a limit notation here as we're approaching 1. Now let's just say we're approaching 1 from the left-hand side, so I'll put a minus sign there. And let's just say this graph is f of x. It turns out that this graph is going to negative infinity. So there you go. If I approach the asymptote from one side, and if I get positive or negative infinity, then that's a vertical asymptote. And it turns out if I approach 1 from the right-hand side now, in blue, if I approach it from the right-hand side now, the function is also going to negative infinity right there. So this is how you can write a horizontal asymptote using, a vertical asymptote using limit notation. Notice that these are particularly one-sided limits now, and now you need to go to positive or negative infinity to justify that you do have a vertical asymptote. Okay, let's just go over a quick example here, and for this question I need to find the equations of the vertical asymptote, and we need to describe the behavior of the function to the left and right of each vertical asymptote. So if I go back to pre-calc 11, I can take the denominator, set the denominator equal to 0, and x would equal to plus or minus 4. So I have two vertical asymptotes, but you have to remember when you have the two vertical asymptotes, a question that was usually asked, a follow-up question that I do ask is how many limit statements do you have to write if you have two vertical asymptotes? And you really have to write 4 limit statements because you have to look at the limit from the left and right of positive 4. And you also have to look at the limit on the left-hand side from the left and the right of negative 4. So you really need 4 limit statements. Okay, so this question is quite a little bit tedious now because you have to write 4 limit statements. And then I would then ask students to go ahead and write those 4 limit statements and figure out what's happening at 4 and negative 4 from each side. Now I'm going to pause the video here and maybe you can think about how to write the limit statements, and then when I come back to the video, I'll show you the solution here. Okay. Okay, so there you go. Those are my 4 limit statements. So if I examine each of these 4 limit statements, this is what it will look like. So I'm looking at 4 from the right and the left, and negative 4 from the right and the left. And these are called one-sided limits because of the plus and minus signs. And you might recall from previous lessons, we want to use the number line technique, and I'm actually not going to draw out the number line just to save a little bit of time here, but when you're approaching 4 from the right, all you're doing is you're thinking of a number on the right hand side of 4, right? So you know what, maybe I'll just draw the number line here, but if you're on the right hand side of 4, you can think of like 4.01, and if you're on the left hand side of 4, maybe you can think of like maybe 3.9, and all you're doing is you're inserting these numbers into the right limit statements. So for the very first one, it would be like 3 times maybe 4.01 all over 4.01 squared minus 16. And you don't need to know the numerical answer. You just know that the numerator is positive. The denominator is positive, and this gives you positive infinity. Okay. For the next one here, this is really 3 times 3.9 divided by 3.9 squared minus 16. The numerator is clearly positive, but the denominator, since you have 3.9 being squared, that's going to be negative after you subtract 16, so that's negative infinity. And then over here, if you're approaching a negative 4 from the right-hand side, so think about that. If you're on negative 4 from the right-hand side, maybe you can have negative 3.9, and on the left-hand side, maybe negative 4.1. So if you're approaching a negative 4 from the right-hand side, just substitute negative 3.9, negative 3.9 squared minus 16. The numerator is going to be negative, and the denominator is also going to be negative, and a negative over negative is going to be positive infinity. And finally, with this last one here, we can type in 3 times negative 4.1 all over bracket negative 4.1 squared minus 16. The numerator is negative, and the denominator is going to be positive, and this gives you negative infinity. Okay. So those are your answers, and if you want to do a little sketch of this graph here, I mean, here's your negative 4, that's your positive 4. If I'm approaching a 4 from the right-hand side, I guess the graph is shooting up like that to positive infinity. If I'm approaching negative 4 from the left-hand side, it's going to negative infinity like that. And then if I draw my vertical asymptote like that, I guess if I approach negative 4 from the right-hand side, the graph is kind of shooting up now. So kind of like that, and then the graph is kind of like that. Okay, so there you go. That concludes this homework video guide on lessons 4 and 5.